So let's talk about some trig functions. We're going to start with some basic angles. I'll show you how to use reference angles to find out trig functions of any angle you ever come across. We'll talk about some graphing of some trig functions, which is going to be kind of interesting. You'll see why they are the way they are, and that should be our day. So the first thing we're going to start with, just a little bit of talk about angles. Now when we say an angle, typically we mean an angle in reference to the x-axis. And we got a couple names for these things. Our angle would be given here. I like to call it theta. Typically, if we're going to start here, this would be called our initial side. What do they call the side where the angle ends?
Terminal.
Yeah, that's the terminal side, of course. You ever see the movie The Terminal? Has nothing to do with angles, but it's a pretty good movie. You should check it out. Anyway, now if we're going to start the x-axis and go counterclockwise, which is the positive angle measurement? Clockwise or counterclockwise? So going this way, counterclockwise gives us positive angles. If we go this way, our clockwise, that gives us our negative angles. So counterclockwise rotation gives us our positive angles. And in converse, we have clockwise giving us our negative angle measurements. Now, when we measure angles, there's typically two constructs for measuring angles. We either do degrees or we do radians. Let's talk a little bit about radians versus degrees. Where do they come from? Why we have them? Radians are kind of interesting. They involve that number pi, which really is a weird number in and of itself, right? I mean, it doesn't end, it doesn't repeat. It's an irrational, actually. Irrational number. It's kind of strange, and it's also a relationship between the diameter and the circumference of a circle, and that's why we want to incorporate that in dealing with angles, because we have parts of circles in that. Then we have this degree system that we also have. That most of the time, that's how we describe angles to each other, right? At least here, we say, if I say, okay, can you draw me an angle of 60 degrees? You have no problem with that, typically. Say, draw me an angle of 3 pi over 14. You go, what? That's crazy. Are you seriously going to draw? Well, you can. I mean, you can draw that, but you don't have that in our heads. So normally, we like to have ways to convert between them, just so we're kind of familiar with them, can use both of our angle measurements. If you're not familiar with this, how our radians and our degrees are connected is with this equation. 2 pi radians equals 360 degrees. The reason why we say they're equal, those are both the way you can represent a circle. So this represents all the measurements degree-wise of a circle, and so does this for radians of a circle. Therefore, they have to be exactly the same. What this gives us, if we do just a little bit of mathematics, if we solve for radians or we solve for degrees, we can even write like this, degrees, it's going to give us a method on how to convert between radians to degrees. So, for instance, if we want to solve for degrees, well, we can divide by 360, and that's going to tell us that to change from radians to degrees, we're going to be multiplying by pi over 360. That works just fine. So, here's our note to convert. If you want to go from degrees to radians, go from degrees to radians, multiply by pi over 180. multiplied by pi over 180. What that's going to do is get rid of your degrees and introduce to you that pi. That's going to change into radians for you. The other way, if we want to go from radians to degrees, well, multiply by, what do you think? Yeah. Yeah, really, you're just multiplying by 1 in a special way. And if you divide both sides by 2, you're going to get pi radians equals 180 degrees. So you're just using that equality to change between our degrees and radians. Would you like to try a couple examples to get your heads wrapped around this? All right, let's change, we'll just do 2 examples really quick. Let's change 200 degrees into radians, and we'll change negative 3 pi over 4 radians into degrees. So 200 degrees. If I want to change 200 degrees into radians, well, I'm already in the degree measurement. I want to get rid of the degrees and introduce the radians. So here I'm going to take my 200 degrees, sure. In order to get rid of those units degrees, you can't have degrees on the top. That's going to be degrees squared, right? That'd be ridiculous. What we want to do is have our degrees on the denominator of that fraction, and that kind of tells you which one of these, if you forget all this, which one of these equalities to use, which one of these conversions. If you're trying to get rid of degrees, have degrees on the denominator. Then your pi is going to be on the numerator, and you'll see that the degree units, those are gone. You can cancel them out just like you would any other variable or amount. Can you reduce that? Sure, go ahead and do that. You've got calculators. If you want to punch in the fraction, just press enter. What is this going to give us? How much?
10 pi over 9.
10 pi over 9, okay. 10 pi over 9 radians. So right there we know that 200 degrees and 10 pi over 9 radians is exactly the same measure of a certain angle. What other angle did I tell you we were going to convert?
Negative 3 pi over 4.
Oh, good memory. I actually made that off the top of my head, so it's good to remember that. So negative 3 pi over 4, all that's in radians, we want to convert this to degrees, which means we want to introduce the degree measurement. What that typically says is, well, we want to get rid of a pi somewhere, so I'm thinking the pi is going to have to be on the denominator of my fraction, and if I want degrees at the end of my problem, I'm going to have 180 degrees on the numerator of my fraction. Does anything simplify out of this?
4 to 180.
Sure, 4 goes into 180, how many times?
45.
Okay. And what, anything else? Ah, the pi's are gone. That's great. Can you do the math? Tell me what we're going to get. How many degrees?
Negative 135.
135?
Negative.
Negative, okay. Sure. Would this angle be measured counterclockwise or clockwise? Sure. Could you find the same angle by measuring some distance counterclockwise? Yeah, angles are strange like that, right? You can go negative or positive and somehow end with the same exact, well, at least reference point. Not same angle, same reference point on that circle. Kind of cool. By the way, speaking of graphing, let's go ahead and go over just a little bit how to graph these appropriately. So if I were to give you, let's try 4 pi over 3. Can you graph that on a circle or on an XY axis? Yes, no? You can you? I can you? How do you do it? How do you do it?
You know, one full circle is 2 pi.
You do. So I know that this is actually pi, and this is 0 or 2 pi. Well, this has got to be pi over 2, and this has got to be 3 pi over 2. Here's the way I always like to graph these things. What I like to do is break up each section of pi into whatever denominator I have. That's the way I think is easiest for me. So I think, okay, if this is 1 pi, I'm counting pi being divided by 3. You see, you can split this up and say, okay, this is 4 times pi over 3. So what I want to do is find out where the pi over 3 sections are, count 4 of them, and I'm going to have my angle. Does that make sense to you? Are we awake today? I know it's Friday, right? You're like, oh, just 47 more minutes, please, or 37 more minutes, please. But stick with me here, folks. This is good stuff. This is trigonometry, right? I mean, some of you, trust me, you need a refresher on this. Believe me. So if I want to break this up in my pi over 3s, I think, okay, well, here's, I split it like that. Here's 1, 2, 3 sections of equal value inside of my pi. Does that make sense? Let's do the same thing down here. So basically, we've broken up each pi into 3 parts, or each 2 pi, each circle, into 6 parts. How many are we going to count? 4. We want 4 pi's over 3. So 1, 2, 3. Our angle is going to end right there. You feel okay with that so far? You sure? Now, if I ask you to graph negative 2 pi over 3, negative 2 pi over 3, we'd start at the same initial side, but we're not going counterclockwise anymore, we're going clockwise. Where's it going to end? You still break it up into 3 parts, right? Every pi would be broken up into 3 parts. If we're counting negative 2, that means we're going to start here, 1, 2. Let's call this 4 pi over 3. This would be our 2 pi over, negative 2 pi over 3. Whenever you have that situation where one angle and a different angle go in the opposite direction and on the same exact terminal side, they're called coterminal. It just means there's multiple ways to measure the same terminal side. I could have gone around like 50 times, right, and then ended right there. It's going to be the same exact ultimate ending spot. How about we graph, let's graph 2 more. Let's graph 5 pi. Then we'll graph, these are a little bit easier, negative 7 pi over 2. So 5 pi, of course we're going to start with our typical initial side. That's our 0 angle or 2 pi angle marker. We've got pi here, pi over 2, and 3 pi over 2. Why don't you try the 5 pi? Start at your initial side. Are you going to go clockwise or counterclockwise? Why counterclockwise? Okay, so go ahead and do that. Count however many pi's you have right now. Now, we don't have to break this up at all because, well, there's no denominator, so we're actually counting 5 pi's. Let's go ahead and do that. How many times around am I going to go? Okay, so I'm going to start here and go, well, here's 1 pi, 2 pi. That's a full circle, isn't it? 3 pi, 4 pi. You getting dizzy yet? And then 1 more. That's going to give us a 5 pi. Looks like a spring all wound up. Do the negative 7 pi over 2 on your own. Of course, you know this is 0 and 2 pi. It's already broken up into pi over 2's for you. That's kind of nice. Well, let's see where we end up. Okay, we'll start at initial side. Negative, I know that means we're going clockwise. I'm going to count 7 pi over 2s going clockwise. That's what our negative says. So here's 1, 2, 3, 4, 5, 6, 7. I know we're that as our terminal side. We've just gone around time and a quarter, or time and 3/4. How many people were able to end with exactly that? Cool. Are there any questions so far before we continue on to some actual trig functions? We're going to put this stuff together now. No? Yes? You all right so far? All right, good. Now, of course, somebody went and said, how can we relate the sides of a right triangle and a unit circle along with their angles? And so we have our unit circle up here. And if we were to make a right triangle out of it, it's a horrible right triangle. There we go. If we consider the point xy, within we're being general here, so we have any coordinates. How far along is this right here? Whatever the x is, sure, okay. And how far is this right here? And if I say the unit circle, how far is the hypotenuse in this case? 1. Good, that's what's a unit circle. Unit circle says has a radius of 1. What someone did a long time ago is they said, okay, we want to somehow represent the sides of a right triangle and call them something. We want to call the ratios of our sides of a right triangle some function, some trigonometric function. So if we have any sort of angle in a right triangle, just like we have right here, and of course you know that's a hypotenuse, and we call this, is this the opposite of the adjacent? Okay. And this is the adjacent side. We had a few trig functions. Let me be real clear before we go any further. The stuff that says sine, cosine, tangent, those are functions, okay? You can't compute those. Those aren't a number. You can't ever just have a, say, I'm going to take sine. Sine by itself doesn't mean anything. Sine has to have some sort of expression of an angle inside of it. If we just say, can you take sine squared plus cosine squared? No, you can't. That doesn't mean anything. This is not equal to 1 because you don't have any angle here. You have to have exactly the same angle for that to be equal to 1. You have to have those angles in there for identities to work, for you to do the computations with them. So if you ever find yourself writing sine and cosine without any inside part, you're probably making a little mistake. Be real careful that sine and cosine have, and tangent and all these trig functions have to be associated with some sort of an angle. Am I getting that across to you? These are functions just based on that angle. Without that, that doesn't make any sense. Okay, now let's go back to this. Let's review. What is sine exactly? It's a relationship between which two sides? Good. Have you ever heard of Chief Soka-Toa? No? Maybe in high school. Chief Soka-Toa, he asks you if you get this wrong. I'm going to ask you a question. Yeah, Soka-Toa says sine is opposite over hypotenuse. And cosine is what? Soka. Okay, and tangent. What's tangent?
Opposite over adjacent.
For sure. We also get the cosecant. You know what, I'm going to write down here so you see a little better. The cosecant, the secant, and the cotangent. They're just the reciprocals of the original 3 trig functions that we have. So which one goes with the cosine? Which one is the reciprocal of our cosine?
Secant.
Yep, the secant is. So here, this isn't adjacent over hypotenuse, it's hypotenuse over adjacent. Well, cotangent goes with tangent. That's going to be your adjacent over opposite. And the cosecant, that's the reciprocal of our sine. So you're going to get the hypotenuse over the opposite. Well, if we apply this idea of a basic right triangle to the unit circle, we actually get ways to compute the sine, the cosine, and the tangent, and all these reciprocals, cosecant, secant, cotangent, of any point that we have, provided we can find the x and the y coordinate. You see, when we apply this, if we look at the sine of this particular angle, look at your angle, tell me what sine is. Sine should be opposite over hypotenuse, right? That's what we define it as over here. What's the opposite to my angle? What's the opposite to my angle? What is it? 1 over 1. Why? Oh, I thought you said 1. It's like, wait a second. We got to review some trigonometry a little bit here. Opposite. Okay, opposite is y over what? Sure. How much is y over 1? Yeah, that's why we get on the unit circle that the y coordinate for that point is sine of that particular angle. That's why we get that. It's our definition now. So sine equals y. Cosine. Cosine should be adjacent over hypotenuse, so the adjacent of our angle is x. The hypotenuse, well that's 1, so we're going to get x over 1 or x. That's why on the unit circle, when you see a coordinate point, x comma y, you know cosine comes first and sine comes second, because we know that the cosine of that angle is the x. It's that distance, which is how we correlate that to any point. So we go, oh yeah, okay, the x coordinate, that means the cosine of that angle. The y coordinate, that means the sine of that angle. That's kind of neat, right? It's the way we combine the idea of a unit circle in our trigonometry. Tangent. Tangent is opposite over adjacent. So in our case, that's the y over the x. Which also leads us to our identity. If you look at that, how much is equal to y over here? Sine. How much is equal to x? You can say it out loud. It's okay to talk in this class. How much is x? If we know that tangent is y over x, y equals sine and cosine equals x, then this also leads to sine over cosine, right? So we get our first identity, tangent equals sine over cosine. That's pretty easy to see. Not too bad. Now you can also do this with our reciprocals here. Instead of opposite over hypotenuse, as far as the unit circle goes, we get cosecant, we get secant, and we get cotangent. They're just the reciprocals of our identities here. So if sine is y, cosecant's 1 over y. If cosine's x, secant is 1 over x. Tangent's y over x, cotangent's x over y. By the way, I would like you to do this. Go in your book and read, not right now, go in your book and read through, I think it's around page 30 through 35, somewhere in there. They have a listing of common angles that we use. It's going to really be helpful to you if I can say to you, give me cosine of pi over 3, and you're able to do it. Give me cosine of pi over 2, I mean at least. Give me sine of pi over 4, things like that. It's going to help you a little bit. So refresh your memory on that. If you need a unit circle right now for your homework, great, but I want you to get kind of in the habit of knowing those by heart or by memory. Can you guys do that for me? At least look them over. Don't go in this class without knowing at least what I'm talking about, okay? Knowing that those exist and how to at least find them.
So you try to memorize the unit circle then?
In your head.
Got it.
Are you guys familiar with what happens to sine, cosine, and tangent as we go around the quadrants? Do you guys know what happens with that? So, for instance, I know that there are 4 quadrants to any xy axis or coordinate system. And this is quadrant, what was this quadrant?
1.
And which one's 2, left or down?
Left.
Good. And so that means that's 3 and this one's 4. We use Roman numerals because, well, I have no idea, we just do. So Roman numerals, that's how we got it, 1, 2, 3, 4. Are you familiar with what is positive in which quadrant?
All students take calculus?
All students take calculus?
Yeah.
Oh. I always thought it was astrology sucks till the crap, but I could do. That's what I would do. Anyway. No, just kidding. Yeah, all students take calculus as a mnemonic to remember that in the quadrants, certain trig functions have certain values. For instance, A means all the trig functions are positive right here. All the trig functions are positive in the first quadrant. Students means sine is positive in the second quadrant. What that also means is that cosecant is positive. All students take, so tangent in the third, that means cotangent as well. And last one is cosine or secant. So all students take calculus. That's not true though. We gotta find something that's true. We gotta think of a better mnemonic for me. Like
Try calculus.
Oh, okay, that was original. Good. Let's see. How about the acronym surrounding this class? I like that. Yeah, that's very okay. Well, you come with something better. Anyway, all students take calculus works just fine. Tells you what's positive in which quadrant. Now, one way that we can use this, if you didn't know, you're like, why do we even we need to know that all students take calculus or know the values of those quadrants? Is we can find out the trig function for any angle using an idea called reference angles in combination with the ASTC, knowing the quadrants. Would you like to see how that's done? Let me show you how that's done. So we're going to talk about reference angles just briefly, then I'll show you how to combine the idea of reference angles with the idea of this, or knowing our quadrants, to determine the trig function and its value for any angle that I give you. Provided you know the unit circle. Okay, that's a must. So reference angles. How to find trig function in any angle is what this is. And the idea is this. What we're going to do is we're going to try to make an acute angle with the x-axis, and then we're going to find the trig function of that, and then use the ASTC idea. Well, we really have 4 cases because there's really only 4 quadrants. So here's what can happen. What I'm going to do is give you a picture, a representation of our angle, and then show you how to find the reference angle. Let's say we start with just a regular angle right there. Is the angle acute? Yeah, then we're already done. Then the angle is our reference angle. So right down here, the reference angle would just be theta itself. You don't have to do anything with that, which means you can find the trig function for that angle pretty easily just by using your unit circle. So that would be our reference angle. However, check it out. If I go past pi over 2, so for instance, this one, is that angle acute or obtuse? What I want to do is find the reference angle. Here's the reference angle. It's just the angle that the terminal side makes with the x-axis, which happens to be acute. So where this is my angle, the reference angle would be this shaded version over here. We just need a way to represent the shaded version right now. So if this is our terminal side and this is the x-axis, how much would this, tell me this, how much would this whole angle be if it went all the way to here? Do it in terms of radians.
Pi.
This would be pi, sure. Now, would you agree that this shaded angle is pi minus whatever my original angle was? That's how we find a reference angle in this case for this quadrant. The reference angle would be pi minus your angle. That's going to give you an acute angle that's formed between the x-axis and your terminal. Nod your head if you're okay with this so far. You see where the pi is coming from. Pi is coming from because, well, that's a measure of pi. We're subtracting our angle. We're going to get that shaded region. Let's keep going. What if we're over here? Can you see the reference angle I want to make right here? This is going past pi and then going a little bit. My reference angle has to be, an acute angle between the terminal side and the x-axis. So what I'm looking at is, this is the whole thing, right? That's the whole pi, or whole angle. I want just this little piece. So let's see. How much is it again from here to here? Okay, now I'm going further, this much further. Would you agree that this angle is all the angle minus pi? Look at the angle. So this is the whole thing, right? And I want to take away all the non-shaded stuff. How much is all the non-shaded stuff? That's pi. So our reference angle here would be theta minus pi. Okay, last one. It looks like Pac-Man a little bit. In our case, our reference angle is going to be this shaded section. Can you think about what that's going to be? What do you think? In order to find the shaded section, we're probably not going to do, well, we could do, well, no, we can't. We're probably not going to do anything with pi, but maybe with 2 pi. 2 pi would be the whole thing.
2 pi minus theta.
2 pi minus theta might work, because 2 pi would be this whole stuff. I'm going to subtract off the theta part. That's going to leave me with that cutout. Not sure if you're okay with that. Yes, yes, okay, good. So reference angle here. Okay, raise your hand if you're okay on where the reference angle idea comes from. You feel all right with it. Good. Now, would you like to see how to actually use it?
Yeah.
Yeah, probably. That might be nice, right? Let's see about that. So let's say I wanted you to find, I'll move over here, get more room. Say I wanted you to find sine, cosine, tangent, secant, cosecant, cotangent of 5 pi over 3. Can you do it? Sure. If you have a unit circle handy, absolutely. If you don't have a unit circle handy, all you would need to do is memorize sine, cosine, tangent of your first quadrant, then use ASTC. That's what I'm showing you here how to do. If you have a unit circle, it's really not a problem. You just go over it, right, and find that stuff. But check this out. If we want to find sine, cosine, tangent of 5 pi over 3 using reference angles, here's how we can do it. The first thing you're going to do you're going to have to locate which quadrant it's in. So in other words, you're going to have to graph it. So right now, as I'm writing down the next step, I want you to graph 5 pi over 3, okay? We just practice that on your own paper, graph 5 pi over 3. The next step after that, we're going to use this idea of reference angles. Find your reference angle. So 5 pi over 3, I'm thinking I got to cut every pi into 3 parts. We've already done that today. I know 5 pi over 3 is positive, so we're going to be going counterclockwise. I'm going to count 5 pi over 3s. So that means I'm going to go 1, 2, 3, 4, I should be ending at that one. Did you end at that one also? Okay, I'm going to erase this stuff just to make it not so bad for us. Right now, I want you to identify your reference angle. Can you shade it in? Just slightly shade in your reference angle. Be careful on your shading. We want something between the terminal side and the x-axis, not the y-axis. Don't care about the y-axis. I want something between the terminal side and the x-axis. So, do I shade this? Do I shade this? Yeah, that's my reference angle. We're actually in this situation right now. So how can I find the value of my reference angle? What would I do? Would I do the pi minus theta, or theta minus pi, or the 2 pi? Which one am I going to do? Sure, I know that this is my angle, my 5 pi over 3. What I want to do is take the 2 pi and subtract my 5 pi over 3. That's going to give me this range. So the reference angle would be 2 pi minus 5 pi over 3. If you do it right, your reference angle should be something that's in the first quadrant. It should be represented in that. So how much is 2 pi minus 5 pi over 3?
Pi over 3.
Yeah, that's it. You have 6 pi over 3 minus 5 pi over 3. That's pi over 3. Are you guys okay with the fraction work? So we've located the quadrant. We got that down. We know it's in the fourth quadrant. We were able to use that to find the reference angle. Now the idea is I want you to find all your trig functions of the reference angle. So find the trig functions of the reference angle. So what I want from you is sine, cosine, and tangent of pi over 3. Anybody know off the top of their head how much is sine of pi over 3? Do you know?
Square root of 3 of 2.
Yeah, that's exactly right. Off the top of your head?
No.
Okay, somebody else. Let's all play along here. Come on, let's do cosine of pi over 3. Yeah, cosine of pi over 3 is 1/2. If you have cosine and you have sine, you should be able to find tangent, because tangent, we just found this out, is just sine over cosine. So if I divide sine over cosine, I'm going to reciprocate and multiply. How much is tangent of pi over 3, please? Perfect. I'm not going to do the rest of them, but you can see that you could do the same exact thing with cosecant, secant, and cotangent, yes? Would you raise your hand if you feel okay with this so far, getting those? Because this is our basic trigonometry. Here's how the reference angle idea worked with the ASTC. If you know what quadrant this is in, you knew that it was everything's positive here, sine's positive here, tangent's positive here, cosine is positive there, and everything else is negative. Here's the deal. Once you have this is the reference angle, right? All we got to do is interpret what quadrant it was in, use the appropriate ASTC, and then we're going to be able to find out sine of 5 pi over 3 and cosine 5 pi over 3 and tangent. So if sine of pi over 3 is root 3 over 2, sine of 5 pi over 3, without doing any more work, is sine, is sine positive or negative in this quadrant?
Negative.
Definitely negative. Why? Well, because the only thing that's positive is cosine. The rest of them are negative. You follow me on that? So here we go, okay, what's sine of 5 pi over 3 then? It's definitely negative, because sine has to be negative there. Have you already found out the reference angle measurement? Just use that measurement with the appropriate sign. Root 3 over 2. I think I've lost some people, because some of you look confused. You're like, I have no idea what's going on here. Let's see, are you okay with STC? That's because someone beat it into your head a long time ago, you just remembered. Are you okay with the reference angles, how to find those? Okay, good. You're just subtracting, or from something, or you're subtracting two quantities to make an acute angle with the x-axis, are you okay that this angle goes to here? And that this reference angle, you have to take 2 pi minus the 5 pi over 3. And what you end up getting is pi over 3. Are you okay with that? Are you okay with getting the pi over 3? Are you sure? I need head nods or something. You can't just
Yeah.
look at me. Okay, yes or no? That's okay too if you're no. Yes? Okay. Can you find sine, cosine, and tangent of pi over 3? You all should be going yes, because that's a necessity to even be in this class. You're supposed to be able to do that, right? You have to be able to do that. Here's the only thing I'm asking you to do. What I'm asking you to do is look at what quadrant that reference angle's in, what quadrant your angle is in. Whatever quadrant you're in, that's telling you what's positive and what's not. You just said you got ASTC, right? Now put it to practice. This is useless if you can't do anything with it. So you know that if my angle was here, everything would be positive. I would be done, because my angle would be pi over 3. If your angle's here, you know that the only thing that's positive is sine. Everything else is going to be negative. Do you get it? If your angle's here, you know that tangent is going to be positive. Everything else is negative. Because sine over cosine, negative over negative, will give you positive. That's why tangent's positive. If your angle's here, you know the only thing that's positive is cosine. The rest of them are negative. Do you get me? You've already done the legwork. You already know the values. This was the hard part. Now you just got to put the signs on top of them. So we're right here. We know the only thing that is positive is, which one's positive for this? Cosine's positive for this. This one I'm going to leave alone. Is sine positive in this quadrant?
No.
I'm going to make it negative. Is tangent positive in this quadrant?
No.
I'm going to make it negative, and that's all I'm doing right here. So I can guarantee you my answers are going to be negative root 3 over 2, positive 1/2, and negative root 3. That's it. Sine of 5 pi over 3 is that, because we already did the reference angle, now we know the sine. Cosine of 5 pi over 3 is 1/2. Why? Because I already did the legwork. I know the value. I'm just trying to figure out the sine. If cosine's still positive there, notice, if you're doing a reference angle, it's all based on quadrant one. Run from this trigonometry stuff. If you're doing a reference angle, it's all based on quadrant 1. That means every number you're going to get is positive. That's why you have to use ASTC to find out whether or not it's actually negative. Do you see the difference there? That's the point. So here I know cosine remains positive. I know sine and tangent do not. So in order to get from the pi over 3 to the 5 pi over 3, I'm not Harry Potter, I'm not the math version of that, right? This isn't magic. It's just using the fact that you used a reference angle, and now you know that if it's in a certain quadrant, what's positive and what's not. Does it make more sense now to you?
Yeah.
Good. That was less anticlimactic than I wanted. I wanted like a, woo, I get it. Can we try that once? No, I'm just kidding. You don't have to do, woo, I get it. But hopefully the energy level will go up for you someday.
How were you when you took your classes?
I don't remember. I took Math 4C in summer school, so that was literally a 6-week blur. I do not remember hardly any of it. I had to go relearn it here. Awesome. Don't do that to yourself if you're going to do anything with mathematics. If you don't give a crap about this, sure, take it during summer school. But if you actually want to use it and you're going to have to use it, don't take it during summer school. Oh my God, unless you're like a superstar at math. Some of you are. Do it, fine. I wasn't. Okay, last thing we're going to talk about today in the last about 3 minutes is a little bit of graphing, where this stuff comes from. What I need you to do is read through, or at least be familiar with your basic trig graphs. Okay, I need you to know what sine looks like, what cosine looks like, and what tangent looks like. Sine goes like this, and cosine goes like this, and tangent goes like this. Okay, and know where they start, what their period is, things like that. You need to know that at least. If you don't know that, you won't be successful with this graphing part. So we're going to graph a couple different types of functions here. We're going to graph things of the form y equals a times sine of some angle, or cosine of some angle. And then I'm going to make it a little bit more complicated than that. Okay, we're going to graph another form probably next time where we're going to make this a little bit more advanced. So for instance, our examples for this. I'm going to graph y equals sine x, just our standard sine curve, and y equals, let's see, 2 sine of 4x. And we're going to see the difference between these two graphs. Firstly, let's talk about sine right off the bat. Where does sine start? That one does, yeah. How high does sine go? What's the period for sine? That means it oscillates every 2 pi. Why? Well, it's on a circle, right? It's going to come back to the same thing every time you go around that circle. That means something important is also going to happen at pi. That means something important is probably going to happen at pi over 2. And something important is probably going to happen at 3 pi over 2. Tell me, if sine starts at 0, what's sine of pi? Oh boy, go refresh your memory on that. What was it? Everyone should just be nailing that. What's sine of pi? You're just copying everyone else. Yeah, you're lucky, it's 0. What's sine of 2 pi? Yeah, of course, because it's going back to the same thing as 0. So sine of 0 is 0, sine of 2 pi has to be 0. What's sine of pi over 2? Tell me that. And sine of 3 pi over 2? Lucky guess. Just kidding. So our function has this nice curve. This is where we get it from. Like that. What we're going to find out next time is what this number does and what that number does and how it changes it. Does it stretch it out? Does it compress it? Does it make the amplitude go different? We're going to find all that out next time. Then we'll talk about this in combination with some translations. That will about end our day, and we'll go on to the last section of our review and finally get to some calculus stuff. You excited? I'm excited. I'm excited. Well, happy Monday. We're going to go ahead and continue talking about what we were talking about, which is graphing some trig functions. Now, the basic ones, I've asked you to read through that. You should know what sine and cosine and tangent look like. This is our basic sine graph. What we're going to do today is figure out what all these numbers do to these graphs, how we can manipulate that. So here's the deal. Whenever we're looking at something of this form, like a sine bx or a cosine of bx, that a and that b, those do something. The a in front of our sine or our cosine, that actually will give you the, do you know? That's the amplitude. That's exactly right. So our a, actually the absolute value of our a, is going to give us our amplitude. And we mean amplitude from the x-axis. So that's why when we graph sine of x, well, there's only a 1 out there. The a is in fact 1, which means that our amplitude is 1 up and 1 down from the x-axis. Does that make sense to you? What's our b in this case? Our b gives you the, well actually it's the period, but what's the b in this particular example? The b here is 4. What's the b here?
1.
And we know that in our case, our period is actually 2 pi. So what we're going to get from our b is our period. So if our b in this case is 1, and our period happens to be 2 pi, then the period is really given by 2 pi divided by b. That gives us how often we oscillate, or how often we come back to repeating the same exact graph.
Is it in that specific example, or is that?
That's in general. So in general, your amplitude is given by the absolute value of a. So in our case, let's look at this example right here. So this is our kind of our notes for right now. What is our a in our case for our new example that we're going to do in just a minute? 2. So our amplitude, absolute value of 2 is 2. That means it should be going too high and too low from the x-axis. Are you with me on that? Okay, so for our example, I'll write this out again. By the way, we need a muffler for your sneezes. As you go, just like that. Shifting gears. Pretty cool. should invent that. See, money right there. Red box and mouth mufflers. Done. Just kidding, just kidding. This works the same exact way for a cosine b. So those are the same exact letters. Those work the same way. So let's look at y equals 2 sine of 4x, and you've already told me that my amplitude, my a, is the absolute value of 2, which is 2. That means we're going to be going up to 2 and down to negative 2. That's what the amplitude says here. We also need to find the period. The period is given by 2 pi over b. What was the b in this case again? 4. So let's do that. Can you simplify 2 pi over 4? Over 2. I need you all to be familiar with how to get the amplitude and the period. Nod your head if you're okay on getting the amplitude and the period in this case. It's good. All right. Amplitude comes from the a, it's just an absolute value. The period is given by 2 pi over whatever our b is. We simplify that. Here's what it means. It means that this example, the stuff in the black writing here, this is going to oscillate or repeat every pi over 2. How you do this, if our entire period is 2 pi here, what we're saying is our entire period is pi over 2 here. It's going to come back to that point after cycling. That's going to be one complete cycle. So can you tell me how many cycles I'm going to get in this range? 4 cycles. That's 4 ranges of pi over 2, 4 intervals of pi over 2. Does that make sense to you? So the period says how often you come back to normal. So it's going to go up, down, and back up. Then up, down, and back up. 4 times in this span. What did this essentially do to it? Did this stretch it out, or did that compress it? Very much so compressed it. So what this did is it compressed it and it stretched it vertically. That's what the amplitude did. So here's how you can figure out how to graph it though. It's going to start at the same spot. So we're going to be at 0, 0. We're going to go up, down, and back up. What happens with these trig functions like sine and cosine is the interesting stuff happens at the midpoints. So if we're coming back to normal at pi over 2, something interesting is going to happen at pi over 4. That's midway between there. Does that make sense to you? So pi over 4, something interesting is going to happen. Okay, and that means, I know this is really small, it's hard for you guys to see it, so this is pi over 4 right there. Pi over 4. How about midway between 0 and pi over 4? How much is that? Pi over 8. So let's cut that in half. Something interesting is going to happen at pi over 8 and 3 pi over 8. That's between here. Pi over 8 and 3 pi over 8. Now, here's how you go the rest of the way. We know that the original function crossed midway between our 2 endpoints here. So midway between at this pi over 4, that's where we're going to be crossing the x-axis again. Can you tell me where the peak of my sine function is going to take place? The peak of my, what's going to be a level of 2, sure, but what's the x value of that? Do you know? Pi over 8, because we know something interesting is going to happen there. In this case, the peak was at pi over 2. If we scrunch this all together, the peak's now going to be at pi over 8. Where's the lowest valley going to be? Where's that going to have to take place? Sure, that's at this one right here. So let me recap for real this time, not just to recap. What we do in this case is we find our A, we find our B. The A is going to give you the amplitude, how high and how low you go. The B is going to give you your period, how often you cycle back to the same exact value and repeat your whole nice function. So in our case here, we know we're going to cycle within a very small window of pi over 2. We know we're going to go up to 2 and down to negative 2. That's going to be my highest and my lowest point. How you figure out the rest of it is just the midpoints of that interval. At the midpoint of that interval, you know something's got to happen. In our case, we're going to be crossing the x-axis again. At the midpoints of those intervals, we're going to be reaching our maximum and our minimum value respectively. So then we can graph it. It's just a normal sine function, only we've stretched it this way and compressed it this way. Nod your head if you're okay with that. Okay, so we're going to be going like this. Wow, that's... like that. That's our compression. We could fit 4 of those in that range of space. Would you raise your hand feel okay with this so far? Okay. Would you like to try one more example to see this before we move on to a translation? Okay, why don't you see if you can do this one? I'm giving you 0.5x, but it could easily be x over 2 or 1/2 x, okay? So 0.5, 1/2, or x over 2, that all means the same exact thing. Here's what I would like out of you. Right now what I want you to do, draw yourself a nice looking graph and draw the original cosine function, just what cosine looks like normally, okay? Just draw that. We're going to erase it, but I want to get the picture in your head. Draw the original cosine function, then I want you to find your A, your amplitude, and I want you to find your period. Do those 3 things right now. I'm going to do it on the board, but you should have it on your paper. Oops. Okay, so before we start dealing with the amplitude and the period, I need you to get the idea, the picture of the function down. So the picture of the function, just the cosine. Where does cosine start at? It goes where? Goes up. Okay, goes up. So cosine would normally start right here at 1 and go like that. Do you have that same graph on your paper right now? You sure? Are you positive? So we know we're not going to be starting at 0. We're going to be starting at either 1 or -1, depending on what the sign is in front of our function. If we've got a negative sign in front of our function, you all should know from just your basic algebra and trigonometry classes that if you got a negative, what that does is that reflects it. Does that make sense? So we're going to have a complete flip. So whereas this would be the cosine function, the negative cosine function would start there. Does that make sense to you? You go up and then back down. That's what that one would do. Okay, so we have an idea of what this is going to look like. It's going to be it's still going to be a nice curve like sine was, only this time it's not going to start at 0, 0. It's going to start at either a positive or a negative number. Now, have you found your amplitude yet? How much is your amplitude? 3. Okay. How'd you find 3? Why isn't it -3?
Absolute value.
Okay, good. So absolute value of -3 is 3. And your period, did you find your period yet? We'd find period by doing 2 pi over whatever our b is. In our case, our b is 0.5. If we divide 2 by 0.5, we're going to get 4. Did you get 4 pi? Do it on a calculator if you have to. 2 divided by 0.5 is 4 pi. Raise your hand if you feel okay with this so far. Finding the amplitude and the period. Okay, good. All right. What that means is that we're going to be cycling from our starting point to our ending point in a period of 4 pi. Not shorter now. It's going to be, what is that? Is that a compression or a stretch? Stretch. That's a stretch. So what you're kind of realizing right now that a number that's bigger than 1 is going to be a compression. A number that's smaller than 1, for example, a decimal that's less than 1 or a fraction less than 1, that's going to be a stretching out. A number bigger than 1 in front is an amplitude gain. A number less than 1 in front is amplitude squishing down. Okay, it's shrinking that amplitude. Do you guys get the idea? All right. Here's
You said less than 1, but does that include -1?
absolute value less than 1.
Less
So
than 1
between 0 and,
Okay.
yeah, absolute value between 0 and 1. That would probably be the best way to say that, right?
Yeah.
Okay, good catch. Now, how do you figure out where to start? Well, do we start at 3? Do we start at -3? What do you think? -3. Why? Well, firstly, there's a negative in front of it. Secondly, why don't you plug in 0? What's 0.5 times 0? What's cosine of 0? Cosine of 0 is 1. Look at you in the circle. You've got to know these things, at least the simple ones. If you don't know sine, cosine, tangent of at least 0, pi over 2, pi, and 3 pi over 2, and 2 pi, you need to go back. Do it today, do it tonight. Make sure you know at least those ones. I mean, those are huge, okay? You also should know the pi over 3, pi over 4, pi over 6. Then you can use reference angles for the rest, but you need to know those at least 4. You with me on that? You got it. It's got to be tattooed on your brain. Hurt, but do it. Or on your forehead, if you read it backwards in the mirror, get it down. Cosine 0, 1, right? So cosine of 0 would be 1. What's 1 times -3? We're starting at -3. So we are starting here. Guess what? If we're starting there and my period is 4 pi, I'm ending there. The interesting things have to happen in the middle of our intervals. That's how these work. So if we have a period of 4 pi, what's the middle of our 4 pi here? Something interesting is going to happen at 2 pi. Is it going to be crossing 0, a peak, or a valley? It's only one of those 3 things. Crossing 0. Remember, I've got to go up, peak, come down, and end here. I'll give you a hint. It's going to be a peak, and the reason is the same thing happens in the middle as it does at the ends. For instance, if you're crossing 0 at the ends, you're crossing 0 in the middle. Are you crossing 0 at the ends? Then you're not crossing 0 in the middle. That's not what's happening. If you're peaking at the ends somehow, either a valley or peak, you're going to be peaking in the middle. So what's going to happen here? Is it a peak or a valley? It's not crossing 0. Is it a peak or a valley? It's a peak. Do you see why? You can't do this. Okay, this is just one repeat of that same number. So here you're going to have a peak of 3. That's the only way that can work. That's the only way you can make one oscillation through that, one cycle, and come up with the same exact ending spot. You can't go up, cross here, down. That would do it. You can't do it on that specific value. It's not going to be crossing 0 there. What's going to happen at pi and 3 pi? You tell me that. That's where you're crossing. At pi and 3 pi, sure. Remember, our original cosine function did that nice swoop. Just that was it. We're just making it bigger and longer. So it's going to go up and come back down. Do you guys see where all these points are coming from? Are you okay with that? The interesting thing has happened at the middle of your intervals. So middle of your interval, that's 2 pi. If you peaked at the ends, you're peaking in the middle. And you're crossing at the other 2 midpoints of those subintervals. So we'll draw our function. Not real pretty for me, but I'm not an artist. So we're going up, come back down. That's the only way we can complete that graph. Do you guys have a basic understanding about how to do these cosine and sine functions now? How many people do feel okay about it? Might take some practice, right? We'll have to look at those things, go back to these notes, watch the videos if you want to. Have you guys all been to the website, by the way? Okay, it's a good place to find at least the homework. And then if you're struggling on some of the stuff, review those videos. Now, there's one more thing that we haven't talked about. We've done stretches and compressions, both with amplitude and with the period. What haven't we done? There's only one other thing. We're going to learn how to shift it. Yeah, that's a whole bunch of shift, isn't it? Oh my gosh. It's fun. Okay, so the amplitude and the period, that's not going to change. But what we are going to do is we're going to take a look at what happens if it's not just bx. What happens if it's like bx minus something?
It'll shift.
It's going to shift. We're going to find out how to do this, how to figure out what type of shift it is, and then we'll do an example. Well, the first thing I need you to do, I'm going to work with this one to show you how it's done, but this right here, this really isn't going to give it to you. It's not going to tell you what the actual shift is. You got to do a little bit more math with that. So here's what we're going to do. We're going to force b to be factored out of those two things. So here's the idea. If we force b to be factored, you're going to write it as y equals, the a is not going to change, the sign, you can't change that. But when I say you're going to force b to be factored out of it, you're going to divide both things by b. If I divide both of those terms by b, divide that by b, what do you get? Good, x. Okay, and somebody else. Divide this by b, what do you get?
Negative c over b.
Negative c over b, very good. Yeah, that we're forcing b to be a factor. Now, whether it actually divides or not, who cares? We're making it divide both of those things. One's going to be a fraction, the other one's going to just be x by itself. Not sure if you're okay with that. See where it's going. Okay. We're going to do the same thing with the cosine. So I'm not going to show the work again. You would just write it the same exact way. This c over b that's where we get our translation. That's going to be a shift along the x-axis. So a shift along the x-axis. Now, it's kind of crucial that you get the shift correct. Gotta get that shift right, all right? Make sure it's fun to say shift, isn't it? A whole lot of shift in this class. What'd you learn? A whole bunch of shift. Letters class, a whole bunch of shift. If you have this, if you have minus c over b, please write this down correctly. If it's minus c over b, like x minus this amount, even though it says minus c over b, what that's going to do, that's a shift to the right. All right, this is defined as subtracting the translation. So this right here, this minus c over b is a shift to the right. So if it's minus c over b, you're going to shift right. If it's plus c over b, you're going to shift it left. I'll explain to you why right now, why this is the way it is in two different ways. Firstly, algebraically, a shift is defined as x minus the shift. So minus the translation, that's a shift to the right. If you had this, check it out. X plus c over b would technically be x minus negative c over b. Do you see that? It'd be minus the shift. That's a left translation right there. That's where that negative's coming from. So I'm not crazy, all right? Plus, I know in your heads you want to go right. But in this case, that plus means left. Another way you can think of it is like a timeline, okay? If you are adding a number to something, you're speeding up when it happens according to a timeline. Timelines go this way, right? With the soonest things happening here and later things happening this way. If you add something to a number, it's not happening here anymore, it's happening sooner than that. Does that make sense to you? You're speeding up when that happens. You're adding something to it, it speeds up when you attain that value. It's an interesting way of thinking about it. If you subtract something like this, if you subtract something, it's slowing it down. It's not happening at year 0, it's now happening later. It's slowing down when that would happen. That's a shift to the right. Does that make sense to you? It's a different way you can think of translations. So we're going to practice this. We only get time for one example with this stuff. But let's practice doing all this stuff with we'll do a cosine. Ooh, doesn't that look fun? Yeah. No, not really. Not really at all. Well, if we look back at the notes that I just gave you, what's the first thing you might want to do? Yeah, you're going to force it to factor. Who said that? Good job. You're going to force it to factor. What number am I trying to divide out in this case? The 2. Very good. That's our b, right? We want to factor out the b. So go ahead and make it happen. I'll write on the board as you write on your paper. Factor the b out. The 3 doesn't change. I want you to write it like this. What should the first thing be?
X.
Yep. It's always going to be x, right? Because you're going to factor that b out of there. It's still going to be a plus. You're not changing the sign at all. Now, is it going to be pi over 2, or pi over 4? Because you're dividing out another 2. Does that make sense?
Yes.
If you do this, if you do pi over 2, which is what you have, divided by 2, which is factoring, factoring is division, what this is pi over 4. You reciprocate and multiply. Does that make sense? Pull that out, reciprocate, you're going to get 1/2 times pi over 2, that's going to be pi over 4. Now let's write out everything that's meaningful about this statement right now. I want the amplitude, so go ahead and do that. I want the period, so go ahead and do that. That's given by your b, remember. And I want you to determine what type of shift this is and by how much. So write out the amplitude, write out the period, and write out the shift. Just think, if you live at home with your parents and you go home and do your homework, and they're like, hey, can you help me with this? You're, no, I'm taking care of some serious shift right now. Right? That'd be a good line. Please, someone try that. It'd be hilarious. Let me know if it works. I always was thinking of those excuses when I was a kid, and none of them ever worked. I wasn't that smart. You guys, now I'm giving you all the hints. Okay, amplitude. How much is your amplitude?
3.
Good, y'all got that, right? Absolute value of 3 is 3. The period is 2 pi over the b. That's the number that you just factored out. So what is our period here? Oops. Yeah, you're right. I almost wrote it right there. Equals pi. All right, the shift. Now the shift. Is this going to be a right shift or a left shift? What do you think? Yeah, even though it says plus, your brain wants to think it's to the right, right? But it's not. It's to the left. This you can think of as it's speeding up, it's happening sooner. That's moving to the left according to the timeline. Or if you think about the definition of what a translation really is, it's minus a negative translation. So that is definitely to the left of pi over 4. Okay, well we got that. I'm going to show this to you. You can graph this with only one graph, all right? But I'm going to show this to you as the original function. This is how I think about it. I think about the original function. I think about the amplified, and this is going to be a compressed function, and then I deal with the shift. Because if you try to do it all at once, it gets a little confusing. You with me on that? So deal with the amplitude and the stretching out and compression first, and then draw that one, and then shift it. So here's what I mean by that. The first thing I know, it's going up to 3 and down to negative 3. The next thing I know, you need to know the period. How much is the period? Okay, so over here I'm going to put a pi, and that's going to be my ending point. I know for a fact that interesting things, I use interesting things are going to happen, which means points that are going to be values or crossings of the x-axis, are going to happen in the middle of this interval. So this is my end goal is going to be this. I know I'm positive because I have no negative. It's going to go down and come back up and end right here. Does that make sense to you? That's what's going to happen. The interesting stuff is going to happen here at pi over 2. Here at pi over 4. and here at, what is that one?
3 pi over 4.
Yeah. Do you feel okay that we're going to be going up and down to 3? Do you feel okay that we're going to complete a complete cycle in pi time, in the interval of pi? Do you feel okay that we need those numbers because that's where the interesting stuff is going to happen? Yes, no? Yes, okay. So let's figure out what this is. Remember, we haven't done the shift yet. We're just going to draw the function without the shift, and then we'll deal with the shift. We'll just move it over. Okie dokie? So let's deal with this function. If I were to ignore the shift for a second, where does it start? 3? It's either 3, because it's cosine, right? It's not at 0. It's either 3 or negative 3. In this case, which is it?
3.
Definitely. You plug in 0, you're going to get 3. Remember, not with that, though. You're ignoring that for a second. So I would start here. That means I'm going to end there. Got it. That means that what happens at pi over 2, is that a peak, a 0, or a valley? You should be able to tell me right now. Definitely a valley. Absolutely. We're right here. What happens at pi over 4 and 3 pi over 4 then? That's our crossings. So my graph should look like... Oh, that's not bad. I got that on video too. Look at that. That's pretty cool. I feel good. Good job, Leonard. Good graph. That's like the best one I've ever done. My gosh. Remember that. It's never going to happen again. All right? This is it. Would you agree that this is my function without the shift? Now, that shift, it said to the right, to the left. Which one? Left. What that means is that all we've got to do is take every key point, boom, 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 all 5 of those key points, shift them pi over 4 to the left, and then redraw it. That's all that means. So fortunately for us, we have almost all the pi over 4s listed, right? That's cool. We just got to make sure that this distance, that's negative pi over 4. You said to the left, so here's what it does. It's the same level, just shifted. Oh, boy. I saw your confused looks. Dang it, that's my 3rd mistake today. I'm past my quota by 1 for the week. I make 2 mistakes a week. That was it. Dang it. Okay. I know, it's Monday, right? That'll be my excuse too. Yes, very good. So what we're going to do is take each of these key points, we're going to shift them 1 interval of pi over 4 to the left, redraw. So we stay at the same level though. So this point was at 0, now it's at negative pi over 4, 3. That's right there. This point was at pi over 4, 0. Now it's at 0, 0. Are you with me on how we're doing this right now? This was at pi over 2, negative 3. Now it's at pi over 4. That's pi over 4, negative 3. Okay, cool. This was at 3 pi over 4. We're going to shift it pi over 4 to the left. That's now at pi over 2. This point was at pi, comma 3. Now it's going to be shifted pi over 4 to the left. That's 3 pi over 4, comma 3. We've just shifted every major point to the left. That's because we have shift to the left of pi over 4. If you redraw it, that'll be the purple line right now. See, I missed. Told you never happened again. We get the actual function. This was the one we copied. You can't do that if you use pencil. Ha 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 ha. But this is our shifted over version. The purple one's the one we need to end with. Would you raise your hand if you're okay with our shift signs? Good, all right, that's good. Did you think they were going to be as nice as this? It's nice, huh? Do it this way. If you've never done this before, this is a good way to do it. Now, what I do need you to do is you need to review your trig identities in the book. I think it's somewhere on page 36 or 37. Review those things. We're not going to be dealing with anything super, super duper hard like some obscure ones, but the basic ones you absolutely must have, like tangent equals sine over cosine. You got to have that. You got to have the Pythagorean one down, where sine squared plus cosine squared equals 1. And the derivatives of, not derivatives, that's the wrong word to use in calculus class, but the corollaries from that, such as 1 minus sine squared equals cosine squared. You need those things, okay? You also need like your half angle and your double angle formulas. You need the ones that say sine of 2x is the same thing as 2 sine x cosine x. You need those. Okay, so review those, have them in your head somewhere, be able to use those things, because we will use them when we're doing integrals and derivatives of trig functions. You need them.